everyone. Trust you all are keeping safe and doing well amid this pandemic situation. So thank you very much for joining us today for Quadro Liquids webinar on mixing of difficult to disperse powders, solving key process challenges of the pharma industry. I'm the Singh from IDEX India. I'm responsible for Quadro Liquids business here. Uh, we have Bactochem team with me on this webinar. And as you know, Bactochem is our authorized channel partner for Quadro Liquids product in India. So from Bactochem team, today we have Mr. Sagar, Mr. Satish Joshi, and Mr. Prashant Vartak. So on behalf of our IDEX team and our Bactochem team, I welcome all our guests in the today's webinar. Thank you very much for joining us. So we will have a very detailed discussion today on key process challenges involving versions of powders like thickeners, energy modifiers for various pharma application and how to address them. So our today's speaker is Mr. Wayne Harwood. Wayne is our national sales manager for Quadro Liquid and based at our Waterloo, Canada facility. So just a little brief on Wayne. So Wayne has a very good hands-on experience working on different high shell mixing application. Earlier, Wayne had application lab, so he has very strong application background. So today he is going to share some good insight on dispersion challenges of tough powders and efficient way of handling them. So I will pass it on to Wayne shortly. Just some housekeeping stuff before that. So for the convenience of everyone, I request all our guests to please keep their microphone during the webinar. However, please feel free to unmute should you have any question or alternatively you can submit your question via chat or use the raise hand button to get the attention. We do have kept 10 minutes for the Q&A. And also please note this webinar session will be recorded and made available on our public YouTube channels as well as on our website video pages. So thank you very much and we really appreciate your cooperation here. So with that, I will hand it over to Wayne.
Great, thank you, Diljit. And thank you again for everyone that's joining us. We know this is, for the most part, at the end of your day, and we appreciate you taking the time to sit with us today and take a look at this topic of our ZC and how we can help you with different difficult to disperse powders and, in particular, rheology modifiers and how they may apply to your industry. So we're going to jump right in, and we're going to start off just with a brief introduction. I know Diljit has already started off by introducing the local team there in India. I wanted to also give you some background on who IDEX is, who Quadro is. And then the Quadro Liquids team in particular in Waterloo and across the globe. Then we'll get into an introduction about the ZC, what it is, how it works, and then we'll jump into 5 different challenges that the ZC is designed to help with. So who IDEX is, really, it is a global company consisting of a vast network of different individual companies through different industries, all with a goal in mind of helping people with different aspects of life, whether it's process operation to health and science operations to different dispensing or kind of even life-saving equipment when it comes to some of our fire and safety products as well. Things like the Jaws of Life are a part of the IDEX portfolio. So we're quite a proud company in terms of being able to influence people's lives in a positive way. consists of many thousand employees. I imagine this is probably actually approaching closer to 7,000 these days, but I haven't seen that updated figure. But what we focus in on, again, those life-saving and impacting of people's lives on a day-to-day basis. Now, within the IDEX portfolio, Quadro is part of a group called the Material Processing Technologies Group, and I'll get into that a little bit further in terms of what makes up that group. But really, we're looking at a lot of, excuse me, the specific process handling equipment, and both semi-solid, solids, and liquids handling equipments. So we keep moving along here. Within the MPT group, there are actually 5 companies. There is the Fitzpatrick Group, the Matcon Group, Microfluidics, Quadro, who we're talking about mostly today, and then as well as Sterados. So within that group, we do a vast or quite a wide array of equipment, everything from compactors to dry mills to powder dispersion, high shear mixing, inline processing, screeners and classifiers, bulk handling equipment, and the most recent addition to the group is Sterados, which will do a lot of sanitary mixing and different processing aspects for liquid processing. So lots of similarities between the groups, lots of synergies, and come together to form that MPT group. Just a quick reminder to mute your mic as we go so we don't get any of that background noise. I appreciate it. Thank you. So moving on, Quadro itself. Quadro is again, part of the IDEX group. We're located in Waterloo, Ontario, which if many of you have had the chance to travel to Canada or not, we're about an hour outside of Toronto, so really close to a pretty major airport there in Toronto, about within that hour. Quadro itself is 170 plus employees currently. We have 2 buildings that we occupy here in Waterloo, where we do both our offices and our manufacturing support for actually a number of the product lines within the MPT group, specifically the Quadro Liquids, Fitzpatrick, Microfluidics, and Sterados, as well as the Quadro Solids groups. So quite a lot of manufacturing goes on out of this one particular facility, and we're quite proud of that. The business has been operating for over 45 years now, and we operate globally. And one of our key objectives is to develop long-term relationships with our customers. That's it means success for both us and most importantly for our customers, because as we mentioned, part of IDEX's motto is to impact people's and customers' lives in a positive method on a daily basis. So delving a little bit further into the Quadro Liquids product line before we get into the ZC in particular and where we fit, we really have 4 main pieces of technology. We have an in-tank mixer called our Y mixer. Then we have the Quadro ZC, which we're going to spend a fair bit of time talking about today. And then we have 2 pieces of inline emulsifying and wet milling equipment, our Z emulsifier series and our HV emulsifier series. And this graphic here just kind of shows us how we relate to, energy scales of the different pieces of technology. Microfluidics, being a sister company, shows up here as well, and they tend to go a little bit further than what our inline technology can do, so it's a great synergy there. So then our Quadro Liquids team, you've met Daljit at the beginning of our call here. He's our sales leader for IDEX India. He handles a little bit more than just the Quadro Liquids line, but I'm sure you may have some opportunities to talk with him further in the future. Myself, who Daljit has introduced as our national sales manager. We also have Andre Paradis, who recently joined us direct from our product lab. He is now our application sales manager. We're in the process of backfilling his position. We also have Wanda Smirnow, who's our technical sales coordinator, and Natish Bardwaj, who's our product manager. So that's our primary liquids team that you may at some point have a chance to work with. So we will move on towards the ZC technology, and to give you a quick look at what it is and why we use it, and then we'll delve into where it can help you the most. So really, the reason why we like to use the ZC is making sure we're picking the right equipment for the right application. The ZC, in essence, has been designed to work with some of those most difficult to disperse powders, things that want to form lumps and fisheyes and agglomerations, because they actually want to grab onto the liquid that they're being added to so quickly that they'll form those agglomerations. And so the ZC in itself has been designed in a way that will allow us to eliminate that from ever happening, to give you a much more efficient process. So when you're dealing with those things, some of the more traditional ways that it's approached is with an in-tank high shear mixer. And one of the reasons, there are many reasons why that doesn't necessarily work to the same level as approaching it in line, and we're going to get into those obviously. But if you're taking a look at this quickly here on this slide, one of the main reasons why in-tank is going to struggle relative to inline is because we've already formed those agglomerations and fisheyes, right? And so there are many problems that go along with having formed those before we want to, and actually trying to eliminate them after they've been formed can be much, much more challenging. So we are going to focus on the reasons as to why that happens. But you'll see in general here, this little graphic down in the bottom right-hand corner, that is what your shear profile looks like inside of the tank. And so you get a very, very wide range of shear concentrated around that high shear mixer. And really you have to get everything down to that point to make it efficient. And that is where your inefficiency will typically arise with an in-tank method. So where's the ZC used? Now this is a really broad spectrum of applications. Not everything obviously here is going to apply to the pharmaceutical industry, but I just want to give everyone a broad sense of places and products that this could potentially be used in. When it comes to the pharma industry, I mean, we're going to see everything from creams and lotions that, do actually apply, cough syrups, different granulation type products as well. Those are all going to be applicable, but we're not limited to those applications either. Really where we want to focus in on is if you have a difficult to disperse powder, whether it is a rheology modifier or it's just even an API or another additive that does not want to add in or dissolve or blend in with the liquid phase that you're adding it to, there's a really good chance that the ZC is going to help for the variety of reasons we're talking about today. So this slide here, we're going to take a quick look at what's actually happening inside the unit, what actually goes into the design to make it effective for those difficult to disperse powders. So as you are feeding your liquid in through the inlet port here on the right-hand side, the liquid is actually shielded from the incoming powder. So that liquid is being fed at a consistent rate, and the disperser actually has a rotor with an impeller or a centrifugal type pumping vane interspersed with the teeth of the rotor and the stator. Now that impeller actually wants to pump away the liquid faster than what we're feeding it. And so that differential created by the disperser is going to create a vacuum, which is going to draw your powder into the process. And again, keeping it separate from the liquid right up until the point of mixing just above the high shear element. And at that point, the liquid and powder meet, the powder is being separated into individual particles, so those lumps and agglomerations don't get a chance to form. And we end up with a really high quality dispersion in a single pass. It's quite effective. So within the ZC, there are actually 4 different sizes of units. Everything from pilot scale, which is our ZC powder disperser, or ZC0, my apologies. Typically a 3 horsepower motor. We're operating in the 3 to 12 gallon per minute range, or it's about 11 to 45 liters per minute. This unit is typically meant for pilot scale, but with many industries, that pilot scale can often be equivalent to more of your production scale. So we actually do see that a fair bit in the pharmaceutical industry because you're often dealing with much smaller batch sizes. So we will see the ZC0 unit used in production, but more commonly when we talk production, we're looking at our ZC1 or ZC3. Those are the most common units, being a 7.5 horsepower motor. You can see the ranges of flow there for the ZC1, and then the ZC3 going up a little bit further. Typically, the ZC3 operates at about 3 times the rates of the ZC1. Pretty simple. Our final scale of operation is the ZC5. Now, generally, this is a very, very large unit, and I would say uncommonly used, especially in the pharmaceutical industry, so we won't spend a ton of time on it. But just for comparison's sake, this might be used to unload something like a silo of powder into a liquid stream. It's going quite quickly when you see the rates of incorporation there approaching 1,000 pounds per minute. Touching here, one of the ways we actually will primarily size the unit is actually based on that powder capacity and how fast you want to incorporate your powder into the liquid, as opposed to a specific flow rate that you want to run. Because we can actually change the rates a little bit by changing the sizing of the tooling that we have installed. And really, we want to provide the customer with the best option. So we will look at how quickly that powder needs to come in to meet your process needs. There's a couple extensions to the individual models that we can include on actually all the sizes here. The continuum or CDS system is our approach to controlled concentrations. And we're going to talk a little bit more about that as we go. But if we're looking at delivering exact concentrations of materials or just a general system that allows you to deliver a controlled concentration over time, we can do that. We can do just the individual unit, or we can do a fully skidded system like you see here in the photo. And then beyond that, we have also developed an ergonomically friendly design for the ZC0, the ZC1, and the ZC3. Again, those are the units that are most common and that you could actually have an operator theoretically keep up with by hand feeding the powder. We simply couldn't do it for the ZC5 because hand feeding 1,000 pounds per minute just doesn't make sense. So this gives your operator a working height of about 42 inches typically, so that they can stage bags right at the top of the hopper and just keep pushing material into the unit at a pretty steady flow. All right, so the first topic we're going to jump into in terms of the ways that the ZC technology can help you is going to be around reducing waste and ingredient losses. I think we can probably guess how that happens, but we'll go over what's really happening here. So this comes back to where we started a little bit. When you get those agglomerations and fisheyes that are happening typically because the powder that you're working with is very hydrophilic and wants to grab onto the water or the material that you're adding it to, so it actually forms a casing around the powder and dry powder inside. For those of you that aren't familiar, that's what we would typically coin as a fisheye. So when you form those, they're very difficult to get rid of. Oftentimes in processes, they need to be filtered out because it simply doesn't make sense to spend the energy, or sometimes you don't have a way to actually break them down effectively to their fully dispersed state. And so many operations will actually filter these out, which is throwing good material away. So if we use the ZC to make that solution right in the first place, oftentimes customers will be able to reduce the amount of material that they're adding, first off, because they're no longer throwing materials away. And second, they can actually eliminate that filtering step from their process, which simplifies things overall, simplifies the cost of the overall application as well. So a couple different benefits that we can focus in on. When you do this in tank, the other thing that happens when you're actually trying to break apart those fisheyes or agglomerations is that you can actually over-shear some of the product. Now, certain products, maybe things like a polymer, like a carbapole or another type of material along those lines, they can be shear sensitive. And if you spend a ton of time mixing high shear in tank after some of the material's already begun hydrating, you can actually start to over shear that and break down the molecular structure of the gel, actually lose the viscosity that you were using this material to try to build. And when we do that, obviously you're going to end up using more material again than you want. So doing that dispersion right the first time with the ZC technology can help us eliminate that over shearing and eliminate ingredient losses, again allowing you to use less of the material that is usually quite expensive. The other thing that we often see with an in-tank approach is going to be buildup on those walls or on the mixer shaft itself. And again, when we do this in line, you're going to eliminate that, which can allow you to reduce the amount of material and still have the same final viscosity build that you see. So when we're doing this, there's a few other benefits that we can talk about too, in terms of we actually are going to use less energy typically than an inline solution because we're applying consistent energy, and we're only applying it to a portion of the batch as it goes through, as opposed to trying to mix that entire batch. We can typically use about 50% less energy. We're going to eliminate that over processing, that buildup on the walls, and we're going to give you a consistent batch to batch product quality. So we have a couple examples of doing this, and this particular one was for a testosterone gel, where we were dispersing carbapole into water, and previously they were actually using a different inline technology. It's an older technology called the tri-blender. Many folks will actually look at the ZC and consider it, hey, it is just a tri-blender. But it's not. It's really the next evolution to that inline technology that is going to take what the tri-blender used to do and do it at a much more efficient rate. So with that tri-blender, they were over processing the materials because they would have to continually recirculate to get everything in. That carbapole, again, many of you may know, it's quite difficult to disperse, and if we're able to do that dispersion right in the first time, we can eliminate all that buildup and filtering of product. And in this particular customer's case, they were able to actually, just based on ingredient losses and the batch time cycle, projected to save almost $300,000 a year. Most of that coming from the batch times. Now, we can see too the ingredient losses were a contributing factor. Per batch, they were throwing away almost $10,000 of material just because of that buildup and that waste. So $10,000 per batch by using, even just a small portion of material that's that lower than what you used to, it will certainly add up quite consistently over time. So we were actually only saving about 1%, but 1% of that material goes a long way. Another example here, again, different carbapole, antibiotic cream. This one we were looking actually strictly at ingredient savings here in the chart on the bottom, but we were able to reduce the overall waste by approximately 2%. Again, by eliminating those those agglomerations, doing this right in a single pass. This was in comparison to an in-tank mixer as opposed to a different type of inline mixer. And so we see the loss, or sorry, the reduction in waste was double what we were able to achieve in the previous example. Moving along here. So the next application or process advantage that we can look at using the ZC is lowering batch times. And we saw a little bit of that on the first example there. The reasoning why, though, so there's a couple ways that we can approach this relative to in-tank technologies versus inline. And if we look at this relative to in-tank technologies, and we do a good dispersion in a single pass using the ZC powder disperser, there's a couple things that are going to happen. We can typically reduce the amount of air that gets added, which means you have to spend less time deaerating a material after the fact, but also just the time to hydrate some of these difficult materials can actually translate to about an 80 to 90% reduction in the batch time relative to some of those in-tank methods, just because we're doing that dispersion right. You don't have those agglomerations that need to hydrate or be broken down after the fact. So this is kind of the most common setup of the ZC or it's actually the most efficient, I would say, but probably not necessarily the most common, because in the pharmaceutical industry, a lot of times you'll have regulated batches that have set amounts of ingredients, and we'll see that on the next slide. But this being probably the most efficient, where you can have a controlled liquid feed coming into the unit, you load your powders up into the hopper, and as that material is being fed to the tank, the liquid material, it goes through the ZC, draws your powders in, goes to your tank, and you finish off any mixing or any maybe other minor additions of liquids or anything else going on to the batch. We'll see this. The reason it's most effective is typically because you have that virgin liquid coming into the unit. It's always at its base viscosity. It's going to be the most effective at creating a vacuum to draw the powder in. So it's not the only way we can operate the ZC, but it does tend to be the most effective way. The next most common is our recirculating setup. So we've got our liquids loaded into the tank already. We're going to recirculate that liquid through the system, drawing the powder in, and then recirculating back to the top of the tank. Now, sometimes if your product or your powder that you're adding, or even the base liquid, is a high viscosity to begin with, we're going to need a couple things here in the system to make the ZC work, and that typically is 2 positive displacement pumps. If the liquid is staying thin, you can actually do this in recirculation without the need for a secondary pump. But as that product viscosity goes up over usually about 500 CP, then we're going to need to put that pump on the discharge of the unit so that we can actually pull away, much like we talked about earlier, how the disperser wants to create it actually wants to pump away faster than the feed to the unit. As that viscosity climbs, we lose that effect. And so we need that pump to pull the material away so we still continue to create that differential and draw the powder in at a consistent rate. So there's a couple different variations of this, is the key point I wanted to make. Some use a pump, some will not. The next key process advantage to the ZC is going to be in reducing the air entrainment. And there's going to be a couple ways we'll highlight here that happens. Really what it is ties back to one of the key points here when we compare it to an in-tank method. In order to actually shear those agglomerations and get that powder well blended into the liquid with an in-tank method, you often need to create a vortex to draw the powder down to the high shear zone. As we mentioned here, it's concentrated around that mixing impeller inside of the tank. So you need to get that material drawn down, and you do that through vortexing. And when you're vortexing, you are constantly sucking air down as well. And that air hits the high shear and will get dispersed into the liquid as well. So this method can actually give you quite a bit of air entrainment. And when we use the ZC, there are a couple ways that we can help eliminate that. Sorry. The first method, well, the most effective we found actually, is with our controlled concentration system. The reason being is we can actually regulate how much the ZC is trying to pump away. So we actually limit to the point of being just about equal to the combined volume of the liquid and the incoming powder. And so that means that we no longer have, or we have very, very little air being added to the liquid at the same time. This particular example here was a system set up for coating solution where we're dispersing a blend of gum and pigment. And the goal was actually to create a continuous flow of the tablet coating solution that has less than 2% of air entrained in the product, because anything more than that would have caused issues when it gets to the spray coating system down the line. So we actually did some benchmark testing when we put this system together. We did a vortexing in-tank system with a high shear mixer down at the bottom to see, like, if you sprinkle feed that powder in, how much air entrainment will you get by creating that batch. And we actually ended up typically about, on that setup, about 80%, about 20% air relative. We had a density of about 0.8 relative to 0.1, which was our target. When we did the exact same test using our ZC with the hopper feed, where we draw the powder in at a rate determined by the tooling and the liquid flow passing through the unit, we actually were able to improve that to about 8% air, so 12% reduction in air through the conventional ZC system, that hopper feed. Then when we moved towards our continuous dispersion system shown here, we were actually able to take that down to about 1%. There's a huge jump from what we were able to do because we were able to, again, tune how much volume the system was trying to pump away relative to what was coming in between the air and the liquid phases. And so that allowed us to get into that target zone and create a continuous dispersion of coating solution with minimal air entrainment. Okay, so the next topic is working with high viscosity. So if we're talking rheology modifiers, obviously that is what we're looking to achieve, is a dispersion of the material that has a lot of viscosity, so that you can hold up your active in suspension, you can hold pigments in suspension, whatever it may be. Oftentimes, those materials are going to have that viscosity to it. There's a good list here of some of the samples and where they might be used in the pharmaceutical industry. Suspensions obviously are one of the top applications listed, but we don't stop there. So, this is a high-level list, but by no means the full list of things that the ZC could be utilized for, or the different products. Just a small sample of things that we've had exposure to over the years. I started to touch on this a bit earlier, but the way we do that is going to be with the recirculating system typically. So when you're dispersing into a really, really high viscosity product, you have to have that dual PD pump system. That first PD pump here, I mean, we say centrifugal in this graphic. When you're high viscosity, that feed pump has to become a positive displacement pump so that you can push the material to the unit. And then your discharge pump has to then be a positive displacement pump as well. And it's ideal to have these partnered very, very closely to the, in particular, the positive displacement pump paired very closely to the discharge. It certainly doesn't hurt to have the centrifugal or the feed pump close to the ZC as well. Now, a couple examples of this in action. We were actually working with a silica addition in this case, where many of you might know silica is very, very light powder, but we were going into a very, very thick base to begin with to add in. The silica is often, at times used in something like, say, a toothpaste or a different type of thick cream, and that base is often already very, very high viscosity. So trying to mix a high viscosity liquid and a low density, very, very light powder can be quite challenging to do. But the ZC does it very, very effectively. And because of that high viscosity liquid, we need that positive displacement pump on the infeed, positive displacement on the discharge. In this case, because fumed silica was so light, the customer also would like to keep from dumping that material directly into the tank. Because it's so light, it could go everywhere. So we paired with them. They would put a powder pump in place to transfer the powder directly into the hopper. We have the hopper sealed off here so the powder can't go everywhere. And that allows us to circulate that liquid until all of your powder has been dispersed. Another example, a skin cream additive. The base was, again, very, very high viscosity. And we've got a system here that allows the customer to recirculate in the main mixing kettle and then transfer all that material over to the next system, basically here. But again, we're using that dual PD pump system with the pumps very, very close together and able to, you can see the inlet comes up here, the discharge is actually coming off the back and then returning back to this tank here. We were trying to actually disperse the active ingredient in this case into a oil and water emulsion base. And so that water and oil emulsion was already very, very high viscosity. And in order to do that, we needed to have that dual PD pump set up in place and able to recirculate around. One of the key benefits to the dual pump setup as well is if you have a product viscosity that is constantly changing as your material is being added, because the viscosity is continually changing, that dual PD pump configuration can actually help us keep the rate of incorporation of the powder fairly consistent. And that is obviously a benefit too, because it allows you to plan your batches much more effectively. Okay, the final, actually, this I believe is the final point that we're going to talk about is controlling the concentration. I think we touched on it also a little bit on some of the others. There are two approaches to doing this. The first being in our conventional hopper feed method. When we are sending the liquid to the unit, we've got a specific set of tooling picked inside of that unit. That will help us define how quickly that powder is drawn in. But if we want to further refine how quickly that powder is coming in, aka decrease the rate of that powder incorporation, usually because the thickener or rheology modifier is rapidly hydrating or something that's going to create a lot of viscosity quite quickly, we're going to want to regulate that feed of powder coming in. And the way we actually do that is by adding some back pressure to the discharge side here. That can be accomplished with a pump. That can be accomplished with a valve and a pressure gauge here. Sometimes it's even just simply accomplished by the natural line pressure of the return line to the tank. But what that does is give us a measurable and a repeatable variable to regulate so that we can tune to a relatively specific concentration. This approach is consistent. It has its limitations though. We can typically tune for many of the rheology modifiers, we can only take it so far with back pressure. So we might be able to go down to certain things, maybe 2 to 3%. If we need to go lower than that in a single pass, we will often need to apply the UFI or the continuous system that we've already talked about a couple times. Because with this method, we are no longer relying on vacuum to draw the powder into the solution. We are using a controlled feed of the powder and a controlled feed of the liquid, and we're going to bring them together in a fashion that they reach the high shear zone without being overly wetted. No agglomerations have formed, but the flows of the two streams are independent of each other. And so that allows us to hit very, very low concentrations, which can be helpful with some powders, but it also allows us to hit very, very high concentrations that we couldn't otherwise do in a single pass. Things upwards of 50, sometimes even 70% in some applications by weight of a solid in a single pass delivered to that next step of the tank. A couple samples of that. We did an SLS solution for this was, if I remember correctly, this was for a gel prep. It was going to be a base fluid for a specific gel. They were looking at 45% concentration, and the ideal was a single pass. Now, we did approach this initially. We tried it with our conventional method. I think the highest we were able to get in that kind of setup was more of about a 20% solution in a single pass. In this case, we were able to achieve a 45% concentration. The gel time was approximately a little less than an hour, with minimal aeration time as well. We did not spend a ton of time in the particular trial here trying to eliminate the air either, but the way we can do that, as we mentioned, again, we use back pressure to apply to the discharge side of the disperser to limit the rate that it wants to pump away. And by doing that, we could have regulated this concentration, regulated the air incorporation a little bit. Overall, this gave us a way to more than double what we could do in a single pass at an exact concentration in a repeatable method. And one last slide here. It just gives us another look at how this is often set up on a larger scale. That the skid we talked about before it's kind of the small scale. It had a ZC0 as the disperser. This is one of the larger units here, and it's a more kind of advanced look at what a bigger system might look like with a loss and weight feeder positioned up above. You've got your ZC down below, and a feed pump, an outlet, a discharge pump there, being able to take away to whatever that next step of the process is. Again, this gives us a way to completely slash batch times. It also gives you a way to run consistently, even in a 24/7 application without any plugging, buildup, or blockages in that powder and liquid interface area. We can continuously run this type of setup without interruption. And that is about all that I had for you today. Now, I don't know if there are any questions on the chat. Daljit, have you been watching to see?
Yes. So we have one question in the chat window, as well as Mr. Ashish Patel wants to ask the question. So maybe I think we can first take the question on the chat window, and then we'll interact with Ashish. So the chat window, it's from Ajit. Usually the powder will be with 0.4 bulk density, which means it already has high air quantity. So in this case, the dispersion of powder results in dispersion of air as well. So how do you take care of it?
Yeah, thank you, Ajit, and thanks, Daljit. When a product is very, very light like that, and obviously, yes, it has air that is in between the powder as part of the bulk density of that material, there really is not a way to eliminate that air from within the product. Because without it, that product wouldn't flow. I mean, you can densify a product by doing some type of additional processing step ahead of the dispersion, whether it's vibration or something to help alleviate the air from the product. But oftentimes there's detriments to doing that. When you take that air out of a product, the flowability of that powder is going to decline greatly. So that I would say that it's usually been densified to that specific bulk density for a variety of reasons. Most often it's for flow. And so we don't usually want to manipulate that too much.
Okay, thanks, Wayne, and I hope Ajit it answer your query. In case you have any follow-up questions, so please feel free to ask. So let's go to Mr. Ashish Patel. So Ashish, you can now unmute yourself and ask your question. Hello, Ashish, you have raised hand, so unmute and ask your question.
He may have put his hand down.
Okay. So thanks, Wayne. I think well on the mixing of tough powder, how ZC dispersion help in quick and efficient mixing, refinement, and as you mentioned, improving the overall productivity. So I just want to wait over here for a while for any further question. So if you have any questions, so please feel free to unmute yourself and ask. Or alternatively, you can also use the chat.
Hello, Ajit here once again.
Hi, Ajit.
Yeah,
Yeah,
Ji.
can you hear me?
Yes,
Yes.
sir.
Yeah. So, my basic question was, when you try to disperse the material already having some air into it, this air also gets distributed, dispersed in a very fine form, which is probably increases the viscosity as well as this air is difficult to be taken care of as a part of a deaeration mechanism or whatever it is when the final product is made. So are there any ways where you can take care of that air which is already dispersed in a fine form? Thank you.
Thank you, Ajit. Yes. Jumping back to my earlier response too, I would say that unfortunately, no. There really isn't a way to eliminate that air that is in the product to begin with. It will get dispersed along with the material, and yes, in some cases, it can be quite fine. And in instances like that, I would suggest that to eliminate that air still requires some type of deaeration step. There really is not a way to eliminate it. What we can help with in terms of eliminating the air is the additional air that can be drawn into a process, not simply the air that is contained within that powder. Because without that air in the powder, it simply would be a solid block that did not flow.
Thank you.
No problem. I think there's another question on the chat about is the system self-cleanable or CIP capable? I would say that yes, absolutely, it is CIP capable. Typically, we will clean the powder or the dry component sections separate because those oftentimes are seeing powders that don't like to get wet. So we often have those cleaned offline. The wetted components underneath the powder valve typically are CIP capable. So we can install a port just below the powder valve. You can toggle flow between the main inlet and the CIP port to clean out the different areas within the wetted system, and that will clean out the system in a CIP fashion.